All right, I think we're live here. Welcome to Urbit Developer Call Series. I'm Mike Osborne, Taller Ravnet. I'm the contributor community manager here at Urbit. I'm the second string taking Josh's place this week, and we have a great talk today. We have Ted Blackman, rovnys-ricfer, and Joe Bryan, who is master-morzod. They will be giving us a conversation today around the Urbit runtime and what's planned for the future, so we can see a little bit of a peek into what's going to be coming down the line. Before we get started, I have just a couple of announcements I'd like to make. So first off, we are going to have, as always, a happy hour after this conversation. It's a little bit less formal. You can go into some details around the conversation or anything else you want to talk to with Ted and Joe. So you're welcome to join us. We'll put the link up at the end of the talk. Secondly, we are always looking for other people and other great subjects for these developer calls. So if you want to speak yourself, or if you have some suggestions on topics you'd like to hear about, please let us know at support@urbit.org, and we would be more than happy to entertain your ideas, because we're always looking for new topics here. Believe me, it's one of my jobs to find people to come to these talks. So help me out by coming up with some suggestions there. And the third thing is today's subject is the runtime. The foundation is actually releasing a few runtime bounties today. So check urbit.org/grants/bounties for our new bounties that we'll be releasing. And if you are inspired by what Ted and Joe talk about today, you can actually dive in and help us get some of this work done. So we really appreciate our community helping out here. So without further ado, I'm going to go ahead and bring on Ted and introduce him.
Howdy.
Hey, Ted, how's it going?
Going pretty well.
Ted's got a pretty distinguished background as a physics degree from MIT. He's been working at Tlon for how many years now?
Almost 4.
4 years now, working in the infrastructure team. So I'm going to go ahead and hand this over to Ted. Ted can introduce Joe, and you guys can take it away. Thanks so much.
Hey, Joe. Joe is also one of the infrastructure developers at Tlon. Been here a comparable amount of time to me. I think you were involved in the project a little bit before I was, but came on in Tlon a little bit later.
Yeah, a little over 3 years formally, but at least a year before that of lurking and trying to contribute as I could.
Yeah, I remember you hosted that discussion on the Urbit white paper.
Yeah, that's pretty fun in retrospect. We had a video call and read through it and speculated as to what it might possibly mean.
Yeah.
Well, I'm fully incepted, and it's all quite obvious, right?
Yeah. I remember asking, why isn't the Arvover event effect protocol spec'd out the way that Knock is? Which I would note that it is still not spec'd out.
Well, that's arguable. It depends on what you mean.
I mean, C code is a spec, right?
No, it's in the kernel. It's just which aspects of it actually flow over the pipe are informal, but it is a subset of a formally specified interface. So,
I think we will get there eventually.
Yeah, we should.
Yeah, so we've got a list of topics to discuss today, and I think we're going to try to run through them pretty briefly and just kind of hit the major topics, and then hopefully have some time for discussion in a more open-ended manner after that. So I'll name the topics very briefly, and then we'll discuss the topics, and then we'll discuss them more. The first one is just sort of what is VER? What is the Urbit runtime? Hit that briefly. What is the current process split? Right now there's the daemon and the worker. What is the event log truncation project, and how will that affect the future process split? Various plans for how Urbit could store more than 2 gigabytes, how Urbit could implement multi-threading, should Urbit listen for nouns on a local socket for RPC, and finally, other possible optimizations and future work. So let's start with, I think we should start with the current process split in var. And maybe you can sort of describe a little bit of what var is in the process of that.
Sure. Yeah. So I wonder if I should do the terminological dive first here. Arvo is Urbit OS. Specifically, it's the kernel of Urbit OS, and it is, sort of the formal, it's the formal aspects of Urbit OS, which is to say that it's this deterministic, reduction of the log of events that happen, implemented in Nock, updating itself, so on, all of the sort of banner item technical features that Urbit implements. The runtime is different from other language and project runtimes in various ways, and in the most general terms, it's just sort of the machinery that makes Arvo actually work, that makes it actually happen. And so we generally think of that as involving two almost completely separate things, right? There is a Nock, interpreter or, execution environment of some sort. And then there is an IO layer that at its most basic, it sources events from somewhere. Those could be, key presses or AIMS packets or other things like that. It applies effects, right? So similarly, that could be a line of output to your terminal or an outbound AIMS packet. And it maintains certain invariants around those events because they must be logged in order to be able to guarantee the determinism of your ship, that you can always reconstruct any state that you were in previously. And so the Urbit runtime, generally speaking, is the combination of those two things, which is to say the Nock interpreter and the IO layer, which involves sourcing events, applying effects, and managing the persistence of the event log.
Yeah, sounds like a good explanation to me. And I think I knew what it was already, but
Yeah.
All right, and I think that's a good segue into the current process split, right? Because right now we have an IO process and a worker process, right? The daemon and the worker. Although I think we're going to move the event log, maintenance of the event log, so writing events to disk and replaying events from disk if you boot up again. We're moving that from the IO process into the Nock worker process. That's right.
Yeah, that's the plan. So let's back up just ever so slightly. We're a little ambiguous when we say var, because we often say it to mean, an Urbit runtime abstractly, but then we also use it to refer to the only complete Urbit runtime that we actually have. So many Nock interpreters have been written, and a couple of different IO processes have been independently implemented. But there's only one project that completely implements all of the parts together, and that is variably var u3, libu3, c king. There are many names. And so that code base, traces its lineage all the way back to Curtis's original experiments over the course of many years as he worked out the details of Nock and, designed the basic architecture of Urbit. There's you can just look through the Git history and see that that code traces all the way back. And until up through version 0.7, that ran as a single Unix process.
When was it 0.7? Or when did we switch to the
we switched to the multi-process architecture in 2018, I think, mid-2018.
Yes, I think that's right.
My memory, if my memory serves me correctly there. And so, you know, like concretely from an implementation standpoint, that project, you know, it's a C project. It involved a custom allocator, a tree walking knock interpreter, a jet dashboard for optimizing, you know, well-known established formulas. All of that was wrapped up in a libuv event loop with drivers, you know, listening on a UDP socket, implementing a TTY interface, that kind of thing. And so there was a single event loop, single process, and everything sort of was kind of, with all due respect, haphazardly sprinkled around that code base. And so the biggest, you know, technical problem, other than just like, you know, complexity and some debt of it being an old code base, was that everything executed on the main loop and therefore blocked the main loop. You know, single-threaded, single process, single-threaded execution. And so computing the knock, you know, for an event blocked the persistence of the event to disk and so on. And so for a couple of different reasons, work was begun to separate that project into two processes that would communicate over local, you know, IPC pipes, and, you know, would both clean up the code base and unblock the event loop, achieve some sort of coarse-grained parallelism in the basic tasks at the runtime. And that project was begun before I came on board, but it ended up being put on the shelf for various reasons. So I took over kind of reviving that and actually getting it out the door. And the basic split is that there was the daemon process, otherwise known as the king, that held the IO listeners with sort of the logical main event loop and managed the persistence of events to disk. And then there was a worker process, colloquially known as the serf, which simply, you know, evaluated events, computed the knock for the events, and periodically, as requested, persisted snapshots of the state. So the state at any given event is a deterministic function of all preceding events. And we therefore have a pretty straightforward log and checkpoint system where we write down each of the events incrementally, and then we periodically snapshot the state. So that was the process breakdown, and it was really quite elegant in a lot of ways. It achieved its goal of you know, some coarse-grained parallelism. It gave us a real opportunity to clean up the code base in a bunch of different ways. And
yeah, I mean, I think it's pretty, you know, good success, right? I mean,
yeah, everybody here has been running it for years, you know, and it's worked reasonably well. So two other things to call out that this achieved. The knock execution itself is reasonably safe, you know, from a security standpoint. There's this deterministic function that it needs to evaluate, and the risks are relatively minimal and can be clearly isolated, right? There's risk of things like buffer overflows and the custom allocator implementation. But we're not sourcing untrusted input in that role. When they were in the same process, however, we were sourcing untrusted input from UDP sockets and things like that. You know, the absence of a barrier there was definitely a risk.
Right. Another way of looking at that, right, is that the you know, instead of taking in data directly from the outside world, which is sort of like a live wire, now the knock worker process only receives, you know, just this one IPC kind of IPC message. There's just one function that is responsible for deserializing that, right? So it's like a few hundred lines, maybe 500 lines, and it's just, you know, one format is deserialized in this very predictable way. And so all we have to do is keep that one function safe, and then that communication layer is relatively safe assuming it can't trigger a buffer overflow somewhere else in the code. But that's much better than just sort of accepting bytes off of the wire, right?
Right, or passing them around through arbitrary layers of the code base where all you have are these buffers, and you have a constant risk of, has this length been validated, and so on.
Yeah.
And so that's yet another win from this this effort. And then the final thing I want to note here was that it was an almost win. But it leads, the almost there leads naturally into the next part of this conversation. And so the worker came so very close to being a pure function of its inputs. Arvo itself is a pure function of its inputs. And so if this IPC protocol is well factored, then all you have are, messages like, here's an event, here's another event, responses back, here's the effects from that event, and so on. And you have this really, really nice interface with very strong invariants that are simple to maintain. But there was two problems, both related to the maintenance of the state. Right? We take snapshots orthogonally, meaning we don't, sort of semantically take the current state of your ship as a noun and serialize that out. Usually, we transparently snapshot pages of the memory allocator, which is pretty cool and gives us fast incremental snapshots and things like that. But what it means is that implementation of the snapshots is coupled to the execution state. It has to be in the process. And the maintenance of that is the maintenance of state, which is to say that it sort of can't be a pure function. It has to write that snapshot out to disk. So here's side effects. And then that snapshot has to be written in coordination with the event log. If the snapshot runs ahead of the log, which is to say you compute an event, and then you take a snapshot, and then you go separately to write down the event, the input, in the event log, and that write fails, you would get yourself into a state where you would potentially have to replay everything because you sort of branched into an alternative, future that would actually take place.
And the difficulty here fundamentally comes from this idea that you're trying to synchronize a piece of state between these two processes, right? Where the piece of state is roughly like how many events this thing has processed successfully and when the last snapshot was taken, right?
Right, yeah. And
right.
You're synchronizing side effects that are caused by these two separate processes. And it's not impossible to imagine doing that, but it is subtle and difficult and, potentially error prone.
Right, and it also means that if anyone were to write a new IO process or a new knock worker process, then there would be extra burden on them to actually, re-implement that kind of synchronization and do it correctly.
Yes, yes. And that's a really good point. This gets to another of the original goals of this effort, which was sort of a good abstraction boundary. So some other project could come along and implement a knock worker, not have to implement all the IO layers, or the IO layers could be implemented in a higher level language that's easier to work in and safer than C, and reuse pre-existing knock workers. And the subtleties of those requirements really militate against that as an approach. We have done it on the knock side. We've done it experimentally once or twice, and then on the IO side, we've done it and released it. And that project is colloquially known as King Haskell. I know many of you are running that. But it was a lot harder than it should have been for a variety of reasons. And so this leads us to the next point here in our outline, which is there's an urgent requirement to truncate event logs in practice. Formally and logically, the state of your Urbit is always a pure function of all the events that have happened to it from the original bootstrap sequence. But there's very little practical benefit to keeping all of those around as long as you can reliably maintain the state. for anyone who's had to have done it, they can tell you that.
I mean, I maintain the state. You mean as long as you have a snapshot that you can trust. So that, okay, I don't have my full event log over the past, years of running my ship, but I have the past week of events and, a couple of snapshots, or even just one snapshot, and then the past day of events, and that's sufficient to start from the snapshot, replay from there, and that way I don't have to go all the way back and replay every time I turn my Urbit off and back on, right? So, and then if I do have that snapshot, even right now, we don't replay any events before the latest snapshot. We start at the snapshot and then replay from there. But right now, there's no way of deleting, not an easy supported way of going and deleting all of the events before then. And so the problem is that the disk ends up filling up linearly over time with all the events, and there's no way to delete the old ones, right? Just sort of a basic. I've always thought of this as just like a very basic thing that your Urbit needs to do. Event log compaction. I mean, this is what any kind of database system that uses an event log has to do this, right?
Absolutely, right. And all of the problems are these kinds of incidental problems. There's issues with the reliability of the incremental snapshots. There's implementation issues with deleting old events from the log. There's synchronization issues with the multi-process architecture. There's just a bunch of, frankly, stupid obstacles to what should conceptually be a very straightforward task. And this,
anyone interested in that should read the fsync gate.
Yeah, and then there's just the whole generic problem of what does it mean to write something to the disk reliably, and is that even conceptual?
One does not simply write a file to disk on Unix.
And so Ted and I have worked together quite a bit at various points over the course of this year, speccing out event log truncation, which really means a new on-disk format for the event log, for the snapshot, making sure that we, if we crash somewhere in the middle of this process, we have enough information on disk to know either where to pick off or to know kind of where to rewind back to. And then I have done almost all of the work involved in adjusting these two process roles and redesigning the IPC protocol. And so the headline version of this is that the event log moves from the IO process to the compute process, and a bunch of things just get much, much nicer. And so that is in a state where it just needs some polish and a little bit of coordination with the other projects out there, most notably King Haskell, and we'll be looking to release that as soon as possible.
Yeah,
and
it's mostly so we move the event log management into what was formerly called the worker, and now both forms of persistence live in that process, and so the IO process has no persistence, right?
Right.
It doesn't read or write from disk.
Right, and it fundamentally inverts the relationship between these two processes, because in what's currently deployed, control resides in the IO process, right? It is the main loop. It is during dispatch. It's maintaining the log, which is
that's
the authoritative source of truth.
And that's weird, right? Because you actually think that the thing that's running Nock should be in control, right? And if maybe I'm pulling in events from Unix, or maybe not, right? Like you can imagine running an Urbit in some sort of stripped down mode where it's only running the Nock worker and not sourcing events, for example.
Right, as more of a pure computational worker. And so this means, among other things, new names for these processes. In the new world, the Nock execution engine and persistence engine is called Mars because it implements and maintains the fundamental invariance of Urbit. It computes Nock, it applies events, it coordinates the management of that state, the snapshot, with the management of the log, and it provides all semantic and security guarantees, basically. And the IO process becomes Earth. URTH, and it does the messy work of mapping our nice, clean, abstract, symbolically represented I/O onto the ugly, messy world of sockets and pipes and TTYs and so on. And just a massive amount of synchronization and coordination logic that used to live in that I/O process just goes away. It is re-implemented on the Mars side, but it's implemented, at the right layer in a way where it all just gets much smaller and more compact.
I'm glad to hear it got smaller. I mean, this is sort of my experiences with Urbit have been basically like, if you make a change like this and you end up with less code at the end and it's easier to understand, then like it was probably the right decision. That's not always the case.
Right.
Sometimes we make a big change and it ends up getting more complicated, and that's a bit of a smell if that happens, right?
Yeah, definitely. And so I will say that I owe apologies to our many pilots out there who have been running out of disk space over the last few months, because this was not the fastest possible way to implement some kind of event log truncation. But I am pretty convinced that it was the right way to do it, that these were actually real prerequisites, that they will make it easier to implement safely, and that they will provide a bunch of other benefits to the project going forward. And so sometimes this is maybe something to talk about in the back half of this talk if we have time, but there's a difficult and subtle balance to be maintained here in working on this project, in that there are real material needs, but there are also both these high-level promises that need to be maintained, and also this long-term vision that needs to be approached. And so we're trying to constantly recalibrate and make sure that we're not working on only one dimension of the problem, to the exclusion of all others. And sometimes that means that we just don't manage to go as fast as we would want to.
I mean, that's the best defensive scope creep that I've ever heard.
Thank you. Thank you. I've been practicing all morning. Do we
every week when our boss asks us, right? It's been interesting, sort of in contrast, working on the software distribution stuff, where we're really trying not to have any scope creep. And earlier this week I had a day where I was like, wait, we need to redo our the way apps communicate with each other, right? We need to change the addressing there. And by the end of the day, I was like, oh no, I fell into it again. Pull out
Yep.
pull out the so yeah, now we're kind of back on that. But it's kind of nice to just have one sort of straight path. Like, okay, we're just going to pound through all the stuff that we know we need to build, and that's sort of a luxury that we actually don't encounter very often, I find, like with the kernel, because often we have to sort of figure out what the premises are, what the premises should be, and Urbit starts from very different premises from everybody else, and those aren't completely fleshed out. So often we have to figure out what those are. And I remember, working with you on this runtime project, like, we had some big questions, like, should timer events be sourced from, should those go through the I/O process or not? Because there's a decent argument that they shouldn't, right? Because they come from Nock originally. Nock asks Ver to run a timer, right? And then, that could just stay in Mars and never go to Earth and back. But that if you start doing that, then it becomes very complicated to figure out, well, which events should live on which side. So if I recall correctly, you decided to keep that going through.
I did for now, although when we get to a later item in your list here, we come up with more compelling practical reasons to separate out events and manage some exclusively in process.
Okay, interesting.
So like there's a teaser for the multi-threading conversation, but I think now we're ready to talk about the famed 2 GB limit.
Yeah, and we should hit that, because that's really, I mean, if there's sort of one problem, this is one of the few things left, in my opinion, that really prevents Urbit from being sort of I don't know, production code or something that like a consumer product, basically. Like
Right.
because we tried to, what?
It's a very unfortunate limit.
Right, because, and basically, yeah, you can only store 2 gigabytes of data total inside of your Urbit. The event log of what has happened to it in the past can grow indefinitely. But at any given time, you can't store more than 2 gigabytes worth of stuff inside of your Urbit. So
yeah, and that's 2 gigabytes in a not
you can't get
particularly compact representation. And what I think a lot of people don't realize, that 2 gigabyte space is also your scratch space. So not only are you limited to the 2 gigabytes for your persistent state, but if you get too close to it, you're going to start running out of room to do work.
Yeah. So this makes it very difficult to keep all 3 of your DVD rips of Shrek 2 in your Arvo state.
The director's cut.
I mean, this is what consumer product means, I think.
Yeah, and so the short answer here is that, well, let me apologize on behalf of the project first, and say this code base should be written in a way where switching between 32-bit and 64-bit representations of noun references is a build time flag, and it's not. Right. So a couple of very good engineers have spent time at various points in the history that I'm aware of trying to get the project into a state, and they have fallen down, rabbit holes, or perhaps they were the homes of other more terrifying creatures. And
as far as I recall, they just kind of worked on it for a few weeks and then gave up because they didn't really want to do it.
Yeah, but I
didn't have any particular problems. They just sort of, it was just tedious.
Well, no, I think it was more than tedious, because if you take the approach of breaking things by changing the representation and then finding all the places you need to fix it, you may never finish. Something that anyone who's worked on this project for a significant period of time knows is that the only way to make progress is to go from a working state to a working state.
Yep.
And so go there implies some limit bounded in time and attention and so on. And so if you find yourself exceeding that limit and you are not in a working state, you really may need to backtrack back to a working state and find a piece of work that is chewable and chew that and get to a new working state.
Yeah. Well, okay, let's take a step back a little bit. So, we've said that you can only store 2 gigabytes in your Urbit, and that includes, any sort of transient memory that's been allocated in the process of handling an event. But that limitation is there. We haven't said why, right? It's not just like a magic number, like, thou shalt not go past 2 gigabytes, or it's not like the block size limit.
Yeah. Do we want to talk about allocators? We can talk about allocators.
Yeah, we should talk about allocators, because right now we have a 32-bit allocator, and there are a couple tag bits on the front of each 32-bit pointer. So we really only have, 30 bits of.
We have a conceptual 30 bits and a practical 29 bits.
Right.
So what we have is 29 bits of word, or 32-bit integer addressing. And if you do the math, that is 2 gigs of data. Again, the 2 gigs is deceptive, because that includes your scratch space, but also because we use a lot of memory to represent cells. So
there are a few problems here, but I mean, I would argue that, so there are a few different ways that we could sort of bump up that limit, right? You did a hack recently and got it up to 4 gigs.
Yep.
We're just like using an extra bit that was sitting there. But then you could also imagine doing various tricks like what the JVM does, right? I think you said that the JVM uses 32-bit addressing, but they're actually able to address up to 32 gigs.
Right. Yep, and this is called pointer compression or reference compression, and it involves maintaining invariance around allocation environment alignment, right? So if you say every allocation points to an even offset into your memory arena, then you don't have to track that low bit, right? you can pass these references around, and then when you go to dereference them, you can left shift them by 1, and they will be correct, right? And so you can do this by any power of 2, right? And the larger your object alignment, the more bits you can save in your references.
Although presumably, if you have, this object alignment, I mean, the sort of bigger the object alignment, the more like wasted space there is in the middle, though, right?
Yeah.
Because typically the object won't be that big, right?
I don't know if we want to go higher than alignment on 2.
You could also do other things, right? So you could say, okay, the first, the first half, right? Everything with the leading bit of 0, all those addresses point to 8-byte words, let's say, but everything starts with a 1 points to 16-byte words, right? I mean, you could do that, right?
Yeah.
The pointer, the sort of pointer offset math is a little bit more complicated, but I don't think that really matters, right?
Right. So we should talk a little bit about what nouns are in U3, and we should be clear that at this point of the conversation, nothing that we're saying has really anything to do with the conceptual nature of Urbit or the fundamental problems of implementing, an Urbit runtime, an execution environment more broadly considered. These are all problems that come with the trade-offs that have been made in the implementation of U3, which is the interpreter that you're running. And so U3 implements a custom allocator, and it's about as basic as a practical allocator can be, with the addition of some like debug and recovery tooling that's a little bit more subtle and sophisticated. But the basic design is a completely classic malloc style allocator. That tracks, it tracks allocation boxes, and it writes the size of the box at the beginning and the end of each box, and it maintains free list by powers of 2, which are just linked lists overlaid on top of the allocation box as they're freed. And if you've read papers, right, because
it's pretty much cribbed right out of K&RC, right?
Yeah, this is just,
yeah.
If you've seen a custom allocator, you've seen this before.
Well, and then there are a couple of things that, it can stay simpler in a few ways, right? Because we have purely acyclic data structures, which are almost entirely immutable, and a sort of pure structured program, or pretty much a pure structured programming, like stack-oriented execution model, right? So everything nests, everything nests sort of completely, right? It's like a tree. There are no cycles really in anything.
Although at the most basic layer of allocator implementation, that's not entirely true, because the runtime, outside of Nock, the runtime uses data structures that don't maintain those same invariants. And we do, in fact, lay arbitrary.
Right, we stick those in this allocator too. Those are, if you ever see the U3 post data structure, that's what that is, right?
Right. And so on top of this pretty basic malloc style allocator, we implement a noun environment, which then has the properties that Ted's referring to, and includes a reference counting layer, includes this unifying equality trick to try to recover structural sharing, and so on. And then it's sort of on top of that second layer that the actual interpreter is built. And of course, unfortunately, these things aren't really layers. If you squint, you can kind of see it in the code base, but they're also sort of all next to each other. It's a personal goal of mine to actually make this layering clear in the code base, because it would make it much easier to understand.
Yeah, that's a good idea.
Yeah, and so there's a type def in the code base, U3 noun, and the type def is type def U3 noun uint32, where we have our own special names for all of the C-sized integer types, but I'm not going to get into that here. And so when you're writing, a function that takes in a noun and does something to it, what you get passed is just conceptually, it's a reference to a noun. And that's a 32-bit integer where the most significant bits are tag bits telling you whether it's a noun, whether it's an atom or a cell, and currently the low 29 bits are an offset into the loom, which is this memory arena where our allocator works. Yeah, and so that's the gist of it. We could make...
And so there are various options for how to try to get more than 2 gigs stored in here, right? So one is what we've described briefly a minute ago of like, okay, you can try to expand the amount of data that can be referenced by these 32-bit addresses, right? And there are a couple different tricks for trying to do that. Another is to switch to 64-bit addresses, which 64 bits should be enough for anybody, right? And then I think, and actually within the scheme, and then the other approach is basically to store some things inside of this loom and some things outside of the loom, right? So then basically one thing that you could point to with a 32-bit reference would be, another pointer to some other arena, right?
Right. Yeah, that's
broadly the categories there.
That's the basic gist of the categories.
And I would say that in terms of the requirements here, it's like, yeah, we have, so most of the data right now is cells, right? Cons cells, pairs, right? So it's mostly tree structure that we're storing, which is a little surprising in some sense. You might imagine that we might just be storing big files, big atoms, right? Text data tends to be just like big atoms, right? Just one big number, like as a buffer. But we don't actually have that much of that right now, despite having, a lot of files in the file system, at least a few hundred. It's not really a lot, but yeah, I think so it turns out that the graph store data structure that's used for storing social data has a lot of cells in it, and our cell representation, as you mentioned, is pretty sparse, right? It's not like we could imagine other ways of representing cells in memory that would use less memory per cell. Maybe by even a factor of 2 or 4, potentially something like that. Maybe not 4, factor of 2, maybe. We might lose other things if we do that, but we could do it. But then there's another, I would sort of respond to that by saying like any kind of trick that gives us a, basically like a finite or small multiplier on how much memory we can store isn't really a good solution, because the idea is that you run your Urbit forever. And so, if I'm running my Urbit for, 100 years, pass it down to my children and grandchildren, they're still running it. If I can only address 32 gigabytes of cells, that's not enough. 64 gigabytes of cells is not enough, right? And that needs to be able to expand to use the something pretty close to whatever the available storage is, right? Like it needs to be in the many terabytes, eventually hundreds of terabytes.
Yeah. I think that's right. And so the short answer is that we need to do all 3 of these things.
Well, I guess I was thinking like if we need to do some more drastic change that gets us to the up a few orders of magnitude up into the terabyte range, then like do we need to do all the other tricks that buy us that squeeze the representations down into smaller?
Yeah. So there's 2 reasons not to go full hog on 64-bit references right now. The first one is that it's messy. It requires a deep understanding of the code base, and will take a lot of time to clean things up. Any place where anybody has cheated, basically, not gone through the proper APIs and stuff. And there's more than a few such places. Although I think I have a pretty good handle on where they are. The real concern there, as far as a solution goes, is that naively switching to 64-bit will make all your cells use twice as much memory. It will mean you get half as much data into your CPU caches.
Right. So it'll slow it down.
Real cost. And dynamic runtimes
actually a lot more cache misses, right?
Yeah, exactly. Dynamic language runtimes really do a lot of work to try to pack things into 32-bit address spaces to the degree that they can. V8 is well known for the work that they've done. We talked earlier about pointer compression. And so the work needs to be done on the U3 code base because we need to have the option. But we don't want to be forced to use it, right? So at least some minimal amount of pointer compression is definitely something we want to be able to do.
I guess the other side of that, though, is like we can probably assume that, you know, for most people, after a while, they're, you know, they will start to use more than 2 gigs or more than 32 gigs. You know, most users will eventually actually have quite a bit of data on there. I mean, think about how much data the average person has on their phone, right? It's probably something comparable to that.
Right.
So I guess, you know, if we say, okay, well, you get nice fast performance while you're storing less than whatever 16 gigs or whatever the cutoff is, but then when you go above that, then you have to switch to 64-bit references, and it gets slow. It's like I also think that's not a great story.
Right. You want other options here, you know, including the pointer compression tricks, but also including ways to move either big linear pieces of data, really big atoms, or less frequently used data out of the, you know, the hot path and onto some slower storage mechanism. And so that's really the big picture answer, is that the fairly straightforward malloc style memory management that is transparently snapshotted is really cool in the way that it works and sort of gets the project off the ground, you know, in the way that a single contributor was able to do. But it's not sufficient for the long-term vision of the project. The long-term vision of the project, this is, you know, in a lot of ways, it is a database engine. And so tiers of storage and compaction and relocation and a lot of the features that a database engine needs are things that we're going to need to. But there's
here's a question, right? If somebody held a gun to your head right now and said, you need to build, you know, a way for Urbit to store 16 terabytes worth of data in it, and snapshots can be slow, but they have to work. But then they have to be incremental, so that you don't fill things up too badly. What would you do?
I mean, I don't know if it's possible to do that without 64-bit references. And you might still need a separate arena for large object storage, right? Because the question really is, you know, what's in that 16 terabytes? And what are the access patterns around it?
All right, so if the same person holding the gun to your head said, okay, now how do you figure out which of those objects go in the large object storage and which don't? How would you implement that?
Don't make me talk about grains.
I didn't say the word.
Don't make me talk about grains. Yeah, so I mean, this is what I mean just by a smarter memory management strategy. Right now, we treat all cells the same. We treat almost all atoms the same, right? If the atoms fit in a 31-bit integer, then they're just, you know, uint32s in the runtime. But if they're larger than that, then they require a heap allocation, and, you know, they're an offset into the loom pointing at that heap allocation, which is some metadata and length, and then you know, an appropriately sized array of words encoding that atom. And it's hard to imagine that type of that level of simplicity in memory management being sufficient. And so you can imagine wanting to take some cells and say, actually, this tree, like the battery of a core, right? It's a piece of code. You basically never arbitrarily, you know, address into it. You only read it all at once. So that
you never ever create mutant copies of it, which is not something you do.
Right. That should be a packed, you know, succinct data structure, you know, optimally represented.
Yeah.
You know, little less sure about what some of the variation in atoms are needed, but maybe in their persistent state, they should be, you know, globally deduplicated, for instance. So yeah, there's a lot that will need to be done, but there are also things that can be done in the relatively near term to bump that limit from 2 to 4 or maybe 8 gigs.
Yeah.
And then maybe to add a large object arena that says, sure, the metadata limit is still at whatever that is, 2, 4, 8.
Yeah.
But you can put individual large object, you can put a, you know, terabyte file in there if you have room on disk. and it'll track the metadata in that unified space, and then the actual data is somewhere else.
Yeah, I mean, I think it's interesting to note that almost everything that we store that's actually large is essentially immutable, right? Like social data in Graph Store, each post there, each each chat message or whatever, right? It's got a signature on it. It's got a bunch of metadata fields hanging off of it, and so it's a fair number of cells for each post, right? It's not enormous, but it's certainly bigger than one allocation cell by quite a bit, maybe 1 or 2 orders of magnitude above that, right? Be my guess. I think it's maybe 2 orders of magnitude above it. Actually, Logan's in the chat. He might know the answer to that off the top of his head. Logan, if you know, go ahead and say it. But and then what are the other big things we've got? Clay files, builds of programs, or batteries rather. So each of those chunks, any big chunk that we have is immutable.
Right.
And so it does suggest that basically, the parts of the kernel that know that they're producing immutable data structures like that, that those parts of the kernel, one easy way to do this might be to say, have the kernel emit a hint, a knock hint, that doesn't affect the result of the computation mathematically, but does hint to the interpreter, hey, throw this into the big the big arena.
Right. It's worth noting, because I'm sure people have run into this before. The word grains refers kind of vaguely to a number of different proposals that have come up around tracking nouns at some kind of lower granularity than just atoms and cells, right? And so from the memory management standpoint, what that means is that in particular for cells, for trees, labeling that in some way, putting a hint on it, there's different ideas of how to implement this. Means treat this entire tree as a unit if you have some way of doing that, right? So you don't have to, you can still concept a bunch of dynamic cells or whatever. But if you have some other path, that's a hint to the runtime saying, I will treat this as a single object in my interaction with it. I don't need full console flexibility.
Right, and then presumably the snapshotting system can take advantage of that too, so that it doesn't have to sort of check whether that noun has changed, or at least you could separate the sort of immutable nouns from the mutable ones, and that way you only have to overwrite the pieces of your snapshot that are mutable, right?
Right. Yeah, and so this is also a big question about the implementation of snapshots. Right now they are orthogonal, which means they're not about the semantics of the noun. We don't say, here's a new noun, I'm going to persist that. Here's another new noun, I'm going to persist that. We just take linear pages of memory at the back of the allocator, and we write them out as pages.
Right, and this is very poor sort of caching properties, basically, right? It's like, which pages are going to get overwritten? It's like quite a few of them in general, right?
Well, but that also depends on other aspects of your memory management strategy, right? So the question feeds into itself. But a different way to handle snapshots would be to handle it semantically and actually say, here's a new noun, here's a new object, or something like that. And that kind of approach seems to require some type of lower granularity tracking of these objects or metadata.
Yeah.
And so I think we're taking a lot longer than I expected we would, which I guess shouldn't surprise me. But we should try to hit multi-threading or parallelism real quick.
So I think that's the one thing left. Like the listening for nouns in a local socket for RPC was in the list also, but we can just ignore that. That's not as interesting. Okay, so let's take the remaining 6 minutes and talk about multi-threading, and we might go a little over. I reserve the right to keep talking. Right now the knock worker is pretty much entirely single-threaded. Maybe there's sort of pedantic exception to that involving libuv thread pools or something, but in practice, the allocator, at least, there's one single-threaded allocator. But there are a bunch of things that we would like to do that would use multi-threading or some kind of parallelism. probably multi-threading, so that because it makes it easier to keep the same memory space. And I mean, I would say broadly there are kind of two big reasons that we might want to do this in the knock worker. One is to kick long-running computations out of the main event loop so that they don't block the main event loop. And we have a few different proposals for how to do that from the sort of knock perspective. From Arvo's perspective, right? Like what events and effects accomplish that. Actually, Joe, you're the best proposal for that I've heard, involving storing a thunk in Arvo and letting the runtime pre-compute that thunk in a separate thread and cache the result. But then also another use case for multi-threading is the fact that the Arvo kernel actually supports two different sort of entry points. One is a poke, where you poke it with a new event, which produces a new Arvo state and a list of effects, right? And this is the sort of main event loop. That's what that does. That calls poke. But there's also peek, which performs a read into Arvo, and it's a pure read in the sense, pure functional read, right? So in the sense that this is just a function that the runtime runs using, against the Arvo state with a path that's the request path, and then that produces a new noun, which does not get fed back into the Arvo state. So there's no write associated with the result of this thing. And we want to use this for remote scries eventually with a remote scry protocol. Sorry, a scry means a read, but it uses our global immutable namespace for that. So it's sort of like Urbit's URL system roughly. So we want to be able to do these, and actually HTTP requests can already use this system, and they can do pure reads. But it'd be great if we could handle pure reads in parallel with writes, so that whenever you do a read, you don't have to stop processing events in order to handle the read. And this should be relatively doable. I mean, as far as multi-threaded allocators go, or like I feel like that's basically the simplest one you can imagine. It's single writer, multiple reader. Everything's transactional, so you have so basically you should be able to build something very similar to an MVCC kind of system, right? I mean, that's sort of how I would approach that.
Yeah, exactly.
It does require changing the allocator in order to support this, right? So how would you, I mean, first of all, do you agree with that description? And then how would you approach solving that?
Yeah, I think that's a great description. And the short answer is that I just honestly don't know. There's maybe two or three. Well, so before I try to go into the details of that real quick, I should note that the guy to really speak to these questions is here in the chat, Fraudwick, and he has done extensive work on knock interpreters in other programming environments, including Jacques, which uses Trull and Gruffle on the JVM, CL Urbit, which is implemented in Common Lisp, and JS Knock, I think is the current operating name of it, which actually compiles Knock to JavaScript, which is really, really cool. My personal view is that there is long-term benefit to a project like U3 that basically takes a nothing up its sleeves approach to everything, so it implements its own allocator.
The C library for nouns and running knock.
Right. We basically, the only dependencies that we pull in are like pure computation things, like we use GMP for some big integer math. We pull in some crypto libraries, and then we pull in libraries for I/O, for an HTTP server, for an event loop, and so on. But we write our own allocator, and we write our own, the interpreter, the bytecode interpreter. Fraudwick is the author of the bytecode interpreter. I think that there is a benefit, even if it's just a research or reference client kind of approach, to a runtime that works, that doesn't depend on something like the JVM. There's varying opinions floating around about that. So I would say, just real briefly, for parallelism, the choice is sort of like to nest different arenas inside the loom that we have, where we have this road system that we didn't have a chance to talk about, but where we recursively nest computations. You could, instead of just, stacking them, you could turn that into a tree. You have various locking and synchronization problems there. It'd be really nice to be able to have multiple separate arenas that could run in parallel, and that would seem to dictate separating, like having multiple looms where one is the persistent state and the separate one is the scratch space, and then you could have multiple scratch spaces going on.
Which also sounds nice in general, right? I feel like that actually cleans up a bunch of things if we separate out, here's the persistent arena versus, okay, when we want to process an event, we create a new arena to run that event. And then also when we want to handle a read request, we create a separate arena. Those both point back into the persistent arena, but then we only have to lock the persistent arena, and that's the only thing that has to be sort of monitored for changes, right? So that for snapshotting,
right?
I mean, it seems to me like and then also that's the arena where we could store all this sort of whatever persistent runtime crap needs to be there potentially.
Yeah. Yeah, a prerequisite to that, in my view, is the same kind of cleanup that would be necessary to handle 64-bit or the pointer compression. Basically, we would have to have real confident control over our representation of references to noun. So maybe we can compress those pointers and get an extra bit where then we say, we can track at least, whether it's in the scratch space or the persistent arena. We would need some kind of encoding scheme if we were going to have multiple arenas. And so,
right.
It is not an inspiring answer, but while I'm confident that there's, ways to do this, it's not close enough, for me where I could tell you what I would do.
All right. Would it be possible, I just thought of this, but would it be possible to have 32-bit references in the scratch spaces, the inner roads, the sort of, ephemeral arenas, but 64-bit in the base one?
Yeah, I think so. There is another noun allocator. If you've run bar meld, for instance, the way that actually works is it reallocates your entire persistent Arvo state in a totally different representation that's off the loom. And that is a data structure also designed by Fraudwith. That is a custom hash consing allocator that globally deduplicates everything as you allocate it. And that is the building block for the portable snapshot system and also for the global deduplicator that we run. It's not a bad candidate for a representation for the persistent state. There are open questions around snapshotting, and it does not currently have a memory reclamation system. You manage away the arena when you're done. It was the bare minimum implementation for the use cases that we have. But it's a reasonable early candidate for an alternative way to store persistent state. But basically,
areas that you get automatic
call to action. If you know about this stuff, if you've read about how V8 manages, because V8 effectively has multiple looms, they're not persistent, they're just worker arenas, and they do it for security isolation so that the references can't travel across these different workspaces. But it's surprisingly similar in various ways. Or if you have interesting ideas about snapshotting allocators, or lots about implementing persistence engines, we would certainly love to talk to you. There is just endless possibilities at this layer.
It's a pretty fun system to work on because it has unusual properties, right? Like, the fact that we have purely acyclic data structures, for example, means that we can actually use just ref counting with no sort of non-deterministic garbage collection, right? No tracing garbage collection. That's feasible in this system. It doesn't mean we should do it that way, but it is how it works right now. And then that determinism is actually really nice for forensics. The deterministic allocator is kind of an unusual phenomenon where it's like, oh yeah, this allocator died in this event, and if I run the event again, it dies in the exact same way.
Yeah, it's a really wild property. I will note it is kind of a hybrid system because we virtualize computations in these nested arenas, and transitions between them involve the moral equivalent of a tracing GC, where we copy out and reallocate anything.
That's a moving garbage collection, right? That step. It's just you don't actually need it. It's an optimization, right?
Right, exactly.
Where there's a lot of work that can be done now that's actually relatively fundamental work on systems like this that haven't really been built before. And so you could have a lot of fun kind of taking the state of the art from V8 and JVM and translating a lot of that stuff into Nock, right? Even just sort of basically Broadwood says Cheney garbage collection. I don't even know what that is, but yeah, it's probably cool. So yeah, I think it would definitely be an exciting project to work on. So yeah, if you're interested, check out those. There should be links to the Urbit grants program, urbit.org/grants, and also talk to Talon about getting a job. All right, we should probably wrap this up. Do you have any final comments to say? And sorry we didn't have a chance to take questions really. Maybe we could take.
I think TACRIGHT Socrip has been doing yeoman's work in the comments here. I've been monitoring them, and it looks.
I have a little bit too, yeah.
I mean, we could have easily spent another couple of hours just on these same topics, let alone following some of the threads that come up. But yeah, I would just re-emphasize Ted's pitch there that first of all, Urbit is awesome, like duh, and strange code style aside, the lower layers of the system are accessible, comprehensible, and it is early enough that you could come in and have a serious material impact. I have had a tremendous time working on this stuff, and would be happy to help anybody who wants to. So please, reach out, check out the bounties, talk to us in the Urbit community or in the Forge or wherever you run into us.
Yeah. All right. Well, thanks for doing this, Joe.
Thank you, Ted. This was a lot of fun.
Yeah. All right. We're gonna hop into the happy hour. Take it easy.